Greetings team, welcome to Module 5. This is all about apportionment. And again, as always, to motivate our understanding of what apportionment is, I'm going to start right off with an example and then build the definitions that we'll need to thoroughly see what's going on here from the example at hand. So example zone happening over here on the right. And right now, for our example, we have the Congress of Parador. Okay, so this is an example where Parador is a small republic located in Central America somewhere, and it consists of 6 states. And so I'm just going to start off a table. And these 6 states are all named, and the names happen to conveniently all start with the first 6 letters of the alphabet. So these states are Azúcar, Bahia, Café, Diamante, Esmeralda, and Felicidad. Those are the names of the states that we're working with. And they each have some population, so there's, I'm going to put a column for total here, and you'll understand what that means in a moment. So each state, of course, has its population. And the total population of all of Bahia is 12.5 million. Okay, so I'm just going to split these up. Okay, so the population, okay, so our populations look like this now. They're 1,646,000. I'm gonna have to put the last 3 zeros for all of these on a second row, which is gonna look kind of funny, but I'm sorry for that. That's just what's happening. So 6,936,000, and now we've got, this one's just 154,000. This one's 2,091,000. And then here we've got 685,000 and 988,000. And here's the issue here. Parador has a Congress, and within the Congress there are 250 seats. So we need to figure out, based on the population of these states, how to divide up the seats in Congress. So this is very similar. You can think of this as relating to the weighted voting system unit, because this is kind of a way of assigning those weights based on our population. So before we start figuring out exactly how to apportion these seats to these states, I'm going to talk about just the terms that we'll need here. So now we're just going to jump into basic elephants. And the first thing is the states. So we need states. And these are the parties that have a stake in the apportionment. In this case, it's just Azúcar and so on. I trust that with the example you'll understand what these are kind of based on the example pretty easily, because they're all named very much after what they would analogously be in an apportionment of seats in something similar to like the U.S. House. So now we've got the seats. And these are the set of identical, indivisible objects. Objects. Yeah. And these are what are being apportioned. So indivisible is important here, right? Because we can't divide up a seat. So you can think in the Congress of Parador, you can't give one half of a seat to Azucar and the other half to Bahia. It's not going to work because you can't like put one half of, we're not like cutting people in half. So we can't do that. So they're indivisible. And now the populations. So I've written out what the populations are for our example, but this is the set of positive numbers which are the basis for the apportionment. So these definitions are such that they're very general, so they don't have to apply to a situation where you're physically giving chairs to people in a government, but the names are very heavily based in that example, but it does not necessarily have to be that. It can be like, hold on a second, I want to fix the camera. It can be something else entirely, but for sake of simplicity, you can just imagine it as actual physical chairs in a branch of government. And so the very last thing is just the apportionment method. And this is just the procedure of dividing the seats among the states. So before we jump into tackling this example, there are a couple more things I have to define, and those are just some calculations that are going to be important to us. So these are important calculations. Cool. So the first is just what's called the standard divisor. And this is the ratio of total population to seats. So it gives you exactly how many people one seat represents. And so this is, we can call it SD. All right. how many people each seat represents. And so this is equal to capital P over capital M, where this is the total population, and M is the total number of seats. Cool, cool, cool. So now we're going to define one more thing, the standard quotas. And this is something that each state has, and it is, you can think of it as the number of seats a state would get if fractional seats were allowed. So this ends up being, let's say we're looking at the state of Azúcar here. We would have, it's denoted with a little q and then sub a for the state that it's specific to. And this ends up being little p sub a, so the population of Azúcar, divided by the standard divisor. So that's pretty clear why we call this the standard divisor at this point. And now with these, we can go ahead and jump into tackling our example. And we're going to do so using, we're going to start with one method, and we're going to go over a few different methods in this unit. And this first method is going to be called Hamilton's method. And so this method was first suggested by Alexander Hamilton, and as humans, we like naming things after ourselves instead of giving things useful names, like maybe a name that indicates how it works or something like that. Nope, we don't do that. We just name things after ourselves because we're selfish. So this, this method involves, and I'm just going to walk through it in the context of this example. The first thing that we have to do for this method is we need to compute the standard quota for each of these states. And so I'm going to put Q here. And what we'll need, of course, before we can compute the standard quota is the standard divisor, which, as you remember, was P over M, population over total number of seats. And so this is 12.5 million divided by 250. And surprise, surprise, this is exactly 50,000. Wow, convenient. This will never happen in real life. You'll never get a whole number with this many zeros. Basically impossible. But things are convenient in textbook land. So we're going to use this. And now computing the standard quota for each of them, we just divide each of the populations by the standard divisor, 50,000. And I want to mention here that this course doesn't require you to buy a textbook. It doesn't require you to get an online license for any sort of portals or anything like that. I do want you to have a calculator that you're comfortable using, though. So it doesn't have to be a graphing calculator, just a scientific calculator with a handful of basic commands so that you can divide things. That's just something that you're going to need. So if you haven't gotten it yet, do it. Okay, so dividing each of these by 50,000, we get 32.92, 138.72, 3.08, 41.82, 13.70, significant figures, and 19.76. And of course, these are all going to sum to 250, the total number of seats. Great. Okay, now what we do for Hamilton's method is we find the lower quota. And that is just a fancy word for rounding down all of these standard quotas. So let's take all of these standard quotas and round them down one. So, and I'll call this the lower quota. And so we'll get 32, 138, 3, 41, 13, and 19. And now these end up summing to 246, so less than the total. Now we're going to make a new row for what's called the residue. And this is just the fractional part of Q, of the quota. So in this case, it's just 0.92. So the residue plus the lower quota equals the standard quota in all of these. So then we get 0.72, 0.08, 0.82, 0.70, and 0.76. And then these all sum to 4, which makes sense because the sum of the residues plus the sum of the lower quotas should be the sum of the standard quotas or the total number of seats. Okay, and now what we do is we rank the states. I like how I'm just extending these vertical lines as we go. We rank the states by the size of their residues. So I'm going to call this residue rank. So this is pretty easy. We just find the biggest residue and count down from there. So we've got 1, 2, 3, 4, 5, 6. And what's going to happen here, and it doesn't make sense to total this, so I'm going to leave this row, I'm going to leave the total column blank for that row. Okay, so now the last step of the Hamilton method is to take our the sum of our residues, these 4 points that, or these 4 seats that were not given to anybody in the lower queue, and we give them in order of the size of the residues. So we take one of these 4 extra seats and we give it to A because A had the biggest residue. And so we end up with A having, and this is the apportionment row. So this is the final thing. So we end up with A getting 33. We give 1 extra to A. Now we give 1 extra to D, Diamante, and so D, they get 42 seats. Now for the third, so we give 1 to the third place, Felicidad, and they get 20, and then the last one we give to Bahia, and so they end up with 1 they end up with 139. And then we are out of seats, of extra seats at that point, so everyone else just gets their lower quota of seats. So 3 and 13. And so that's how the Hamilton method would work here. We take just to recap, we take the lower quota. So we find their standard quotas, we round them all down, and then we write out their fractional parts. We figure out how many seats are left, which is either the sum of the fractional parts or the sum of the seats minus the sum of the lower quotas, either way. So you can see that either by summing the residues, or you look at the sum of the lower quotas and see that it's 246 and you need 250 seats. So either way works for that. And then you give away one extra seat at a time to the states in order of the size of their fractional parts or their residues. And then you end up with all 250 seats, or however many seats, apportioned in whole numbers to each of the states. Cool, so we've now seen how Hamilton's method would apportion the seats among these states. Now we're going to talk about a different method, and I wonder what it's called. I bet it's named after somebody and not named anything useful. And you probably guessed it, it's named after Thomas Jefferson. Because we know that these two just love to argue about ways to do things, or if you're a theater kid, you probably think that they like rap battled or something. Yeah, if you're a theater kid, I'm just gonna have to ask you to chill for a moment, because the rap battles, they'll start at some point. At some point, we'll have rap battles. Don't worry. So this Jefferson's method is now all about finding a divisor, not necessarily the standard divisor, and it's definitely not going to be the standard divisor, but we find a divisor that allows the lower quotas to sum to the total number of seats. That probably sounds really confusing, so I'm just going to do it and you'll see what happens. So we're going to start off with the standard divisor, and here's what's going to happen. So I'm just going to erase the bottom of these columns, but for those of you at home, you'll probably want to make a new table for this and just rewrite these numbers. I'm actually, yeah, okay, so what happens now is we'll start with the standard quota. And what we're going to do is we're going to modify the divisor such that these lower quotas end up summing to 250 somehow. So we undershot here. We're starting with, we actually should rewrite Q, and we should write Q and then D equals 50,000. Because that's what's going on here. We've got Q when D equals 50,000. And now we've summed our lower quotas, and we've gotten something that's less than 250. So what's going to happen now is we're going to make D smaller and then repeat the process of making these two rows with the smaller D, and then see what the lower quotas sum to. So I'm going to do Q and then D equals 49,000. So now I'm redoing this process of dividing the population by a divisor, but now I'm doing it with 49,000. And what that gives me is 33.59, 141.55, 3.14, interestingly enough, 42.9, 13.67, 13.97, and 20.16. Cool. And now I'm not going to worry about what those total to. It's not going to be 250 anymore. It's going to be something else. But that actually doesn't really matter, so we don't have to fill it out. Now we're going to take the lower Q, which corresponds to this row now. So we're just going to, once again, subtract off the fractional part. So we get 33, 141, 3, 42, 13, 20, and now we're going to sum those up and we get to 252. Okay, so when we try to give out seats in this way, we're going to give away too many seats, and somebody is going to get seats that don't exist. So the next move is to make our D higher and see what happens then. And this process is essentially going to repeat until we find a D that gives us lower quotas that sum to 250, like I've said a bunch of times. So let's go ahead and try Q where D equals 49,500. Okay, so using this, we're again just going to modify each state, or we're going to divide each state's population by this number now, this D, and so we'll get 33.25, 140.12, 3.11, 42.24, 13.84, and 19.96. And now we're going to find the corresponding lower quotas to this. And we're going to get, so lower Q. And so this is now 33, 140, 3, 42, 13, and 19. And this does in fact sum to 250. So we have found a divisor which gives us lower quotas that sum to 250. So this is now our apportionment. So this is an example. There's a flow chart associated with what happens here. So I'm going to talk about that. So it starts with a start. We're going to, the start is always guess a divisor, where the divisor is less than or equal to the standard divisor. The standard divisor is always guaranteed to undershoot, so it's best to actually start with something that's less than the standard divisor if you want to skip a step, but either way you'll get there. So that's our starting block, and now we're going to have a computation block. And so this is, there are going to be 3 smaller blocks within this block. And so there's, first is divide the state's populations by the divisor. So I'm doing P sub S for P sub state. then round numbers down, that's not a word, round numbers down, and then add numbers, then the total equals t. And now one of three things will happen. If you get t is less than m, like we did the first time, then you make d a smaller number. Make d smaller. And go back and start over. And if you get that t is bigger than m, like we did our second try, then you make d a bigger number, and then if t equals m, then you are done. So a little bit more complicated, the Jefferson method, but it does get you there eventually. And you can make these educated guesses for d based on what you got before. And then that will be everything for this coming class Tuesday, and we'll work through some examples related to that. Thank you for watching. Peek the quiz and make sure that you've use that to make sure that you know everything that you should from this, and we'll work through stuff in class.